Great. Well, thank you, Valentin and Stefano, for organizing this very nice workshop and for the opportunity to speak. So we all tend to think that our eyes provide us with very reliable information about the outside world. But in truth, the sensory signals that they provide are rather noisy and incomplete. For instance, consider driving in your car and you're trying to estimate the distance to the car in front of you. Now let's say you estimate the distance to be about, let's say, 40 meters. But it could of course also be 30 meters or perhaps even 50 meters. In other words, your perception of distance is actually consistent with a whole range of values. And this range can also change. For example, when driving at night, when our perception is consistent with a much wider range of values, then we're typically much more uncertain of our estimates. Now, how do people make decisions on the basis of such limited and uncertain data? How do we do this? So, one of the outstanding questions in this field of perceptual decision making is how uncertainty is represented in cortex. And theories of neural coding propose that uncertainty is reflected in a probability distribution that's encoded by whole populations of neurons. In other words, when visual areas get activated by an image, these areas do not represent a single distance, but rather a whole range of distances, where the width of this range reflects the degree of uncertainty. But the question is, and this range of course can also change, for example when driving at night. But the question is sensory information indeed encoded probabilistically? Is this the neural representation of uncertainty? So what we're going to do today is ask three questions. First, can we measure the uncertainty associated with stimulus representations in human visual cortex? Can we measure these probability distributions? 2, do human observers also rely on this uncertainty when making perceptual decisions? So do they use probabilistic information in their decisions? And 3, if so, then how does that uncertainty affect our perceptual decisions? And this work was carried out by Ruben van Bergen, who is now a postdoc in my lab. At the time he was a graduate student with me. All right, so first things first, can we measure the uncertainty associated with stimulus representations in human visual cortex? So the way we approach that question is as follows. We had 18 human observers perform the following task while they were in the scanner. So there was an orientation, a stimulus would come on, there was a brief interval, and then there was a response window in which they would report the orientation by rotating this bar. Now let's focus on this response window for a little bit. Let's say this was the actual orientation presented on that trial. Now let's say the observer reported on that particular trial this particular orientation here. So this is for trial 1. For another trial, they reported a slightly different orientation, right? Because there's a little bit of noise in the system. And on trial 3, yet another orientation. So what we have then across trials is a distribution of behavioral values, right? And what we're going to do is we're going to focus on on behavioral variability, so the standard deviation of that distribution and the mean of that distribution in this talk. So those are 2 behavioral metrics that we're going to focus on later on. All right, so while the observer was viewing all these orientations, we recorded their activity patterns in cortex. And of course, what we'd like to know is what kind of information is represented in these activity patterns, right? Can we measure these probability distributions? So what we're going to do is we're going to see what kind of information we can decode from these activity patterns. And the way we approached that was as follows. Let's say we have these 2 voxels here in early visual cortex. The voxels that of course are indirectly measuring from whole populations of neurons in cortex. Now what we can do is we can plot the response of one voxel against the response of another voxel. And that's shown up here, right? Now this is for trial 1 for a given orientation. We can do that for a second trial for the exact same orientation, a third trial, and a whole bunch of trials for that exact same orientation. Now, this is orientation 1. We can of course also do that for another orientation shown up here, and a whole bunch of other orientations, even though they're not shown up here. Now, looking at these response distributions, a few things are immediately apparent. One is that voxel responses are variable, just because of noise in the measurements, in the MRI measurements, but potentially also because of neural noise. And because voxels are variable, they're actually consistent with a whole range of orientations. And that becomes very clear when we look at this independent test trial shown up here. Now, if the goal is to infer what orientation caused that response, right? If we don't know what the response or what the orientation caused it and would like to infer it, then we're in a little bit of trouble, right? Because it could be either orientation given these distributions. But what we can do is we compute just how likely either orientation is given this particular response, right? And that's what we're going to do. So this is the probability of one orientation. This is for another orientation and for all orientations in between. Where this, of course, is the most likely orientation estimate given that particular response. And this is the degree of uncertainty in that estimate. So what do we have then? There's trial 1, there's trial 2, and we can decode or measure these, compute these probability distributions, right? Now, maybe trial 1 was a little bit less noisy, and trial 2 was perhaps a little bit more noisy. And then that's also reflected in these probability distributions, right? So what we have then, in effect, is a measure of trial-by-trial uncertainty. Now, this is the general approach. Let's zoom in a little bit and look at the generative model, so the specifics of our decoding approach. How did we model voxel responses? All right, so we assumed that each voxel contains populations of orientation selective neurons. And of course, these neurons have tuning functions, shown up here. So these are the modeled tuning functions of the voxels. Now, this is of course at the neural level. At the voxel level, we'll see a mixture of different populations. So that means that we should also observe a mixture of neural tuning functions. So this is for one voxel. Of course, for another voxel, we can do that too. That's shown up here. Slightly different mixtures, a slightly different tuning function. You can do that for yet another voxel, and a whole bunch of voxels. All sorts of modeled tuning functions for the voxels. All right, so with this in hand, let's see what the model then predicts for a single trial, single voxel given orientation, shown up here. All right, so we have these neural population tuning functions, right? And given this particular orientation, the red dot here represents the predicted response, average response of the red population. So that's for the red population. We can look at the green population, the blue population, all shown up here. All right, so those are the average responses, right, for tuning. Of course, at a single trial, we have noise. So that's where we're going to add neural noise that's also correlated. And this correlated noise actually turns out to be quite important, although I'm not going to talk about that today. So if you guys want to hear about that, just approach me after the talk and I'd be happy to explain. All right, so with this correlated noise, then we arrive at this particular response profile, predicted response profile, at the neural level, right, for a single trial. All right, so that was the respondent neural response. Of course, what we'll observe at the voxel is somewhat different, right? It's a mixture of those responses, and that's shown up here. Now, this is the voxel's neural response. Of course, also at the MRI level, we'll have noise, so we're going to add that to arrive at this particular response at the voxel level. So this would be the observed response. Now, of course, this is just for a single trial. Across trials, we'll have a response distribution, right, because there's noise for different trials. This is for a single voxel. We can also do that for multiple voxels, and then we'll arrive at a multivariate response distribution, and that's shown up here. So this is the modeled response for a given orientation. Yeah? And just for comparison, this is the actual response that we observed. right? So this is for orientation 1. We can also do that for another orientation. And then when we have this particular independent test trial, we can use this modeled distribution, these model distributions, to actually compute the probability of a given orientation, or for each orientation given this particular response. Yeah? Does that make sense, everyone? How we use this to compute probability distributions? All right. So now that we have this, let's see what we can do, right? Let's apply it to our data and see what we get. All right. So what do we have? The distribution for a given trial, right? We can decode this from actual MRI activity patterns, where this is the orientation estimate, and this is the degree of uncertainty in the estimate. And we can do that for one trial, we can do that for another trial, a whole bunch of trials, all sorts of distributions, right? And these distributions, they vary in width, right? As they should, because there is noise in the MRI measurements. They should vary. But of course, the question is, are these distributions meaningful? And the reason why I ask this question is because there are two sources of noise. There's MRI noise and there's neural noise. And of course, what we're interested in is this neural noise. So the question is, do these distributions reflect something about the noisiness of the cortical representation, right? Can we actually measure the neural noise at the level of fMRI voxels? Now, we reasoned that more precise representation in cortex should also result in more accurate behavior, which is kind of intuitive, right? And what that means is that if we can actually, if the decoded uncertainty reflects the uncertainty of the cortical representation, then decoded uncertainty should also be linked to behavior, right? So that's what we're going to test for. And we did that in two different analyses. So for the first analysis, we relied on a well-established behavioral phenomenon, which is that behavioral orientation judgments are more precise for cardinal than oblique orientation stimuli. And we also observed something similar in our behavioral data, where the behavioral variability for cardinal orientations was lower compared to oblique orientations. So this is called the oblique effect. And we wondered if something similar was going on in our decoder. So with smaller decoded uncertainty, we also observed smaller decoded uncertainty for cardinal compared to oblique orientations. So that's what we're going to test. So what do we see? So we clearly do see that decoded uncertainty was smaller for cardinal than oblique orientations. So this is the first piece of evidence to suggest that the decoded probability distributions reflect the reliability of the underlying cortical representation. Yeah? So this was pretty encouraging, and we wondered if we could push this even further by focusing on a single orientation. So the question is, does behavioral variability also increase for decoded uncertainty irrespective of orientation, so with orientation constant? Yeah, so that's what we're going to test for now. All right, so what do we see? This is when decoded uncertainty was low, so very narrow posterior distributions, where the single dots represent single observers. This is where decoded uncertainty was high, so very broad distributions. And this is for in-between levels of uncertainty. And clearly our answer to this question is affirmative, right? Behavioral variability does increase with decoded uncertainty. So that suggests that we can decode probability distributions that reflect the uncertainty in human visual cortex on a trial-by-trial basis. We have a metric for the precision of a cortical representation on a single trial of data. Yeah? And I should also mention that the stimulus properties here were held constant. So it's really internal variability that renders the stimulus more or less certain, right? It's internal noise, so to say. Yeah? Make sense? Everyone? All right. So that brings me to the second question of this talk. Do human observers also take this uncertainty into account when they're making perceptual decisions? Is this the neural representation of uncertainty that we use in our decisions? Yeah? So that's where we're going to test for now. All right. And the way we tested this is, again, by relying on another well-established behavioral phenomenon, which is that observers tend to report stimuli as being tilted away from the cardinal axes. In other words, if this is the actual orientation, then observers tend to report this particular orientation, again with a certain distribution shown up here. So now we're talking about biases in the mean of this particular distribution. Yeah? So this is an example observer, and we see clear biases away from the cardinal axis, away from 0, 90, and 180. Clear biases away from those axes. Yeah. Now, we do not really know what the neural mechanisms of these repulsive biases, but we do know that theoretical work predicts that if uncertainty in visual cortex is used, if this is the uncertainty that we use in our decisions, then this bias should increase with uncertainty. So that's what we're going to test for now. All right, so the question is, do we see larger behavioral biases with increasing uncertainty in cortex, right? So what do we see? This is where the coded uncertainty was low, so very narrow distributions. This is where uncertainty was high, where again, but the dots represent single observers. So this is where uncertainty was high, so very broad distributions. And this is for in-between levels of uncertainty. So we see a clear link between behavioral biases, the magnitude of these biases, and uncertainty. In other words, this suggests that human observers appear to use internal uncertainty in their perceptual decision making. And this is the first piece of evidence to suggest that this may be the representation that we use in our decisions. Yeah? And that brings me to the third question. How does that uncertainty affect perceptual decisions? Yeah? And that's where we're going to test for now. Are there any questions so far? All clear? All right. So let me first take a step back before we're going to address that question. And let's go back to our driving example to illustrate the general framework that we're going to be addressing this particular question in. Now, let's say, you focused at the road markings down here. So you focused at the line here, and then you made an eye movement and an eye movement back. And of course, the orientation of this line hasn't really changed much, right, while you were making these eye movements. Because the external environment is, of course, fairly stable from one moment to the next. But sensory signals, on the other hand, are rather variable and uncertain, right, as we've just seen. So let's say your representation when you first looked at the line was something like this, right? It's consistent with a whole bunch of orientations shown up here. But then maybe the second time you looked at the line, there were these, clouds that cast a shadow over the road, and that caused your representation to change slightly. Or maybe, you just tilted your head a little bit, and that changed your representation. Or maybe, the wind caught a hold of these leaves and dropped them closer to the line, and that also caused your representation, right? Or maybe you just weren't paying close attention, and that caused some internal variability. Now, there's all these ways in which the representation can change from one moment to the next, right? And from the brain's perspective, that's not great, right? Because it makes it very difficult to infer what is the actual orientation of the line, right? So a reasonable question to ask then is, are there ways in which this uncertainty can be reduced, right? Now it turns out there's several ways in which uncertainty can be reduced, but what I'm going to focus on today is this notion that the external environment is fairly stable from one moment to the next. because it turns out that in a stable environment or a predictable environment, uncertainty can be reduced by combining sensory observations. At least that's what you can show mathematically. So let me illustrate this. So if this is the range of orientations given the current input, then mathematically, so that the ideal, and this is the estimate based on the current input, then the ideal observer does not base their estimate on just the current input. Rather what the ideal observer does is the observer uses previous input combined with some knowledge about the temporal natural statistics to make a prediction, shown up here. And then it combines that prediction with knowledge about the current input to arrive at a new distribution, shown up here, where now this is the optimal estimate. And you can show mathematically that this actually will give better estimates if in a natural environment, right? It really makes you better, more accurate in terms of your decisions. But the thing is, it also generates small biases in your estimates towards previously seen orientations. And moreover, because the ideal observer relies more on input that is more reliable, that also means that if your representation becomes more uncertain, these biases should change. So in other words, the magnitude of trial-by-trial biases depends on uncertainty. And we can even quantify this more explicitly in a Bayesian ideal observer model, where we not only find biases in behavior that depend on the difference in orientation, we also find that these biases should become larger with greater uncertainty in cortex. Now, this is just a mathematical model. This is just what you ought to do. It's a normative model. This will give you the best possible behavior. But of course, the question is this also what human observers do, right? So that's what we're going to test for now. So we have two predictions. Behavioral orientation judgments should be biased towards previously seen orientations. And two, the magnitude of these behavioral biases should depend on uncertainty in cortex. And what we're going to do is see if these two predictions hold. And the way we did that was as follows. So we had 18 human observers perform the following task, again, while they were in the scanner. So there was an orientation, a brief interval, and a response window in which they reported the bar or rotated the bar to report orientations. Now, if we enlarge that bar for a little bit, let's say this was the response of the observer of that particular trial. This was the actual orientation. We can compute errors. Now, we can do that for one trial. So this is trial 1. We can also do that for the next trial. Orientation, brief interval, orientation, or response window. This is the reported orientation. We can compute the error. Just for reference, this is the previous orientation. So what we're going to do now is look again at biases in this distribution, right? All right. So first, are these orientation judgments in terms of behavior biased towards previously seen orientations, right? Or first predictions. So what we're going to plot is positive values reflect errors towards the previous orientations. And what do we see? We see a clear bias towards previously seen orientations, right? Replicating previous studies. So in other words, these behavioral orientation judgments are biased towards previously seen orientations. Our first prediction holds. But of course, the real interesting question is, does the magnitude of these biases also depend on the degree of uncertainty in cortex, right? Because that suggests they would actually be, use this representation of uncertainty in their behavior. So what we're going to do is we're going to decode these probability distributions again, right? Much like we did before using our methods. And we did that from area early visual cortex, so areas V1 to V3. So what do we have then? We have two bins. We're going to divide the trials into two bins. one for which the current representation was more certain compared to the previous. And then we have a second bin of trials where the current trial was a little bit more uncertain compared to the previous trial. Yeah? And of course the question is, do we see changes in the magnitude of these biases, right, as predicted by our model, by the ideal observer model? All right, so what do we see? Just for reference, this is what the model predicted, right? Clear pattern of behavioral responses. What do we see? This is where the cortical representation was more certain on the current trial compared to the previous. And this is where the current representation was more uncertain compared to the previous trial. So in other words, we do see clearly larger behavioral biases with greater uncertainty. And that suggests that human observers integrate past and present information in a statistically advantageous manner. Right? So they appear to use probabilistic information in their decisions. All right, so what do we have then? So we can use MRI to characterize the trial-by-trial uncertainty and perceptual representations. We have this metric for fluctuations in the internal representation. And two, observers also appear to rely on the precision of their internal knowledge in their perceptual decision making. So they appear to use probabilistic information. And then finally, a word of thanks, most notably to Ruben van Bergen, who did all the hard work on this project, and thanks to you for all of your attention.
I wonder if you can go a bit further than that and exploit the fact that the optimal model or the ideal model makes not only a qualitative prediction but also a quantitative prediction about the increase in uncertainty and how it should relate to the increase needed to the effect of biases or
Yeah, that's a very interesting suggestion. So the idea is to actually use the uncertainty that the model gives, right, to predict the actual size of the magnitude of the bias. The thing is that what we're decoding is changes in the width of the distribution that's due to both, neural noise as well as fMRI noise. And that latter part is a huge chunk. So it's actually very difficult to get at the precise degree of neural noise rather than just changes in the magnitude, and that makes it difficult to do that particular analysis. But I can see where you're coming from.
I guess if you use not just two levels of noise but greater range,
so
you can have some equivalent noise methods.
So what we did here, and I should have mentioned it, is we didn't actually manipulate external noise. We relied on fluctuations in internal noise. So in that sense, we actually do have that range. But if you, just pulling it apart in two bins is the most sensitive analysis.
Thank you for your talk. I have a question about how the precision of the signal that you decode trial by trial is related to the strength of the signal.
Yeah, so that's an excellent question. We looked at that to see if the decoded uncertainty was related to the overall bold response. And we didn't find any correlation there. So that suggests that at least rules out certain SNR explanations or even like a simple attentional count, because we know that changes in fluctuations in attention also increase the bold response.
Hi. Very impressive. Related question. So I was wondering, how do you cross-validate the decoded answers? And so another question is, so if you just decode orientation, how accurate are you?
Okay, so we do cross-validate, obviously, and for decoded orientation, I actually have a slide. Let me see. So that was basically decoding the most likely orientation, right? This is an example observer. This is for, so on the left is for a given observer V1, on the right is across observers. So it's fairly consistent with what others have found. Yeah. More questions?
Clarification, but I did not quite understand how you manipulate the uncertainty of the
Mm-hmm.
and why you are assigning a single point to each subject. I mean, you are assuming that the subject is holding the same level of uncertainty throughout the.
All right, so what we did here is we relied on internal fluctuations in the representation. So we didn't have an external manipulation, we really relied on internal fluctuations in the representation. And there's a number of reasons why we did that. One is that, of course, we're measuring in visual cortex, right? So if you have an external manipulation, it's also going to change, things in a bold response in sort of like uninteresting ways. So that's one reason. The other thing is that we really wanted to rely on trial-by-trial fluctuations, right? In a way that the observer could not use some sort of heuristic. So for instance, if you use the contrast of a stimulus, then that could actually, because we know that like for a lower contrast stimulus, we're typically not as good. They could use that as a heuristic to uncertainty, and we wanted to rule out that particular explanation, which is why we kept that stimulus constant to really make sure that that we were decoding uncertainty as opposed to something else. Does that make sense?
And you are assuming that's kind of a constant for each subject?
No, so we assumed that would fluctuate across trials, and that's why we looked at behavioral variability, because uncertainty and variability should be directly linked.
But in a couple of diagrams, you have like one single point per subject.
That's right, yeah. So we did this basically in a regression analysis across subjects. Yeah?
I'm curious about whether you think there's since the uncertainty is only represented as neural noise, or it may be represented as firing rates in some other region, like probably more frontal or higher up in the visual hierarchy.
Yeah. So you're asking about what kind of what the fluctuations mean in terms of processes or where they come from?
So you've said that uncertainty seems to be encoded in the neural noise, in the variability of the bold response, right?
Mm-hmm.
Have you seen, or do you think it might be also related to, not to the variability, but to the average firing rates in some other region maybe?
So that's actually an interesting idea. So the thing is that for this particular, so what we did for these particular studies is we focused on early visual cortex only. So we didn't record from higher level areas because that was just going to make us a little bit more sensitive. But we are currently actually recording from the whole brain and see if we can actually see what areas read that information out and how that information is then transmitted to other areas and used in decisions. Yeah.
Do you have any expectations about that?
So I think some of the other presenters from yesterday can probably better answer that question. We know that there's areas that read out that signal, right? At least in the monkey, there's area LIP that's been involved in that. There's frontal regions, so we're looking at those regions. But yeah, maybe you guys can better address that question than I can.
Thank you very much.
Two more questions.
Hi. Do you make a distinction theoretically between perceptual noise and representational noise? And if I assume kind of what you're measuring here is a representational noise, and if that's the case, do you think that kind of has a fall-off effect, so that if you manipulated the interval between stimulus presentation and the response, that you would see differences with different intervals?
Yeah. So I'm not sure if I fully understand your difference between perceptual versus representational. So I do know that at least for when you look at the variability of behavioral responses over time, so if you increase that interval, then people do become more variable. So there is definitely a working memory component to that particular aspect. That's not what we look at here. Yeah?
Thank you very much. You were able to relate the variability of visual cortical responses to orientation. Did you try looking at the variability of motor cortical responses and relate that to the behavioral variability? And would you make a prediction that the correlation is stronger between the behavior and the visual variability or between the behavior and the motor cortical variability?
Yeah. So we didn't look at that. We only covered the occipital cortex early areas. But presumably there's many sources of noise, right, that go into this, decision. And sure, yeah, motor noise would be one of those sources of noise. So my prediction would be yes, there would be portions that are related to motor noise. But it's an open question.
Okay, thank you again, Janneke, and I think it's coffee break now.
All right. Well, thank you.